Math 1314, Tyler Junior College, section 3.4, zeros of polynomial functions, the rational zero theorem. In the previous video, we kind of discovered where the numerators and denominators of the zeros of a function were embedded in the original function. In fact, I still have the last two statements written. The numerators of the zeros were embedded in the constant term. When I say embedded, I mean that they multiplied to make the constant term, so they were factors of the constant term. The denominators of the rational zeros, of the zeros from the previous function, were embedded in the leading coefficient. So they were in the leading coefficient as factors. We can take this and codify it into something useful, something called the rational zero theorem. The rational zero theorem states the following. If f of x is a polynomial function, so a bunch of powers of x's, where the powers are whole numbers, with integer coefficients, so the numbers in front of the x's are positive or negative whole numbers, no decimals, no fractions, no messy things like the square root of 2 or pi. If f of x is a polynomial function with integer coefficients, then all rational zeros have the form, that is a giant fraction bar, factor of the constant term, translation. The top of the fraction has to be a factor of the number at the end of the function. That's on top. In the denominator, factor of the leading coefficient. So, the denominator of your rational zeros must be a factor of the front number, assuming your function is written in general form from highest power to lowest power. Well, this is pretty powerful stuff. Because if we're not told a zero of a function and we need one to find a good synthetic division problem, meaning a remainder of zero, just guessing a number at random will probably not work. But this tells us we shouldn't. We should only look at numbers of this form. So we're going to make what's called a list of possible rational zeros for two functions. The first function we're going to use is f of x equals x to the third power plus 2x to the second power minus 7x plus 4. The second, we'll call it g of x, is going to be 3x to the third power plus 5x to the second power plus 4x minus 2. Now, notice I'm not being asked to actually find any zeros. I'm being asked to list the possible rational zeros. When you are asked to do that, you're making a list of things that might work, and you may or may not find ones that actually do work. In other words, you're making a list of numbers that might make the function equal to 0. You may or may not be asked to actually find some that do. To make a list of possible rational zeros, which I'm going to abbreviate from this point forward because we're going to be doing it quite a bit in this series. I'm going to abbreviate possible rational zeros PRZ. So to make our list of possible rational zeros, see if I can find a better red marker than this. God, I didn't make the trash can, going for a blind shot there. That's a little bit better. For the list of possible rational zeros, we start by listing factors of the constant term on the top. The constant term is the number at the end, if it's in general form. More specifically, it's the number that doesn't have a variable on it. So the constant term, being 4, means that we want factors of 4 as possible numerators. The denominators are factors of the leading coefficient. The leading coefficient is 1. So in the denominator, we want factors of 1. Well, this is going to be a pretty easy list to make. In the top, we need to list every number that will divide into 4 evenly. And it seems like it's only 1, 2, and 4. That's only half the list. Because at no point did I say these factors had to be positive. They could be positive or negative. So if 1, 2, and 4 are factors of 4, then so are negative 1, negative 2, and negative 4. Now, I don't have to list them separately. I can just stick a plus minus in front of each one, So now my list actually has 6 factors in the top, 3 of which are positive, 3 of which are negative. The denominator is even better. What's the only factor of 1? Well, I say only factor, implying there's only 1. 1 is the only positive factor of 1, but anytime a positive number is a factor, so is its negative. So the only factors of 1 are plus or minus 1. And now I just have to make every possible fraction by picking a numerator and picking a denominator. Luckily, the only denominator I have is plus or minus 1. So I have to put each of these numerators over 1. That's easy. 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4. This pencil sharpener's in the way. But each of these are of the plus-minus variety. So what does that mean about this function? That means that if I had to guess a number that was a rational number, meaning a ratio of integers, which could reduce to an integer, if I had to guess a number that makes this equal to 0, there's only 6 numbers I need to try. 1, -1, 2, -2, 4, and -4. So I've limited my guesses from infinity to 6. That's a big jump. Let's try the second one. The possible rational zeros for g of x equals 3x to the third power plus 5x to the second power, plus 4x minus 2. To list the possible rational zeros, in the numerator we list factors of the constant term, and the constant term here is -2. And in the denominator we list factors of the leading coefficient. The leading coefficient is 3. So, what numbers will divide into -2 evenly? 1, 2, and their negatives. So plus or minus 1, plus or minus 2. And what numbers will divide into 3 evenly? 1, 3, and their negatives, so plus or minus 3. So unlike the previous list, we have multiple denominators, so we need to set up all of our possible ratios. The way I like to do this is to pick one denominator and then run through the numerators. So let's list everything that's going to be over 1. 1 over 1 is 1. 2 over 1 is 2. Both will be plus minus. These are what I call my over 1s. Now I have to do my over 3s. So 1 over 3 is 1/3, and 2 over 3 is 2/3, both of which will be plus minus. So, if there is a rational zero of this function, translation, if there is a whole number or fraction that will make this equal to 0, it is in that list. Now, one thing that's worth pointing out, there is no guarantee which of the numbers are the actual zeros. There is no guarantee which of these 8 numbers will make this function equal to 0, if any of them. Same thing here. There's no guarantee any of these 6 numbers will make that function equal to 0, or which one will. This is just a list of numbers that might work, so it's still kind of a guess and check game, but at least we've narrowed it down to 6 and 8 possibilities, respectively. So again, when you make a list of possible rational zeros, they are precisely that, possible rational zeros, numbers that might work. How do you find out which one works? Well, we could substitute it into the function and see if it comes out 0, or equivalently, we could use the remainder theorem, which says if we substitute a number into the box in synthetic division, the remainder will be the same as substituting the number into the function. Which will I prefer? The remainder theorem. I'd like to see which of these are actually zeros by substituting them into the box in synthetic division. Why? Because if it is a 0, I need to use synthetic division to factor, so I might as well have it ready. Alright, so rational zero theorem, list of possible rational zeros, integers and fractions, ratios of integers, that could make a function equal to 0. Again, no guarantee which ones, if any of them, work. It just narrows down your guesses from random to a finite number of values.